start of the Geoconfluence, we thought it would be ideal to get some students involved. And so we've reached out, as we have each of the previous 2 years of Geoconfluence, to our partner universities, Missouri and then, of course, SMT. And we have a speaker from each of those schools. And to let you know that the schools actually kind of have a runoff, if you will, or a competition to determine who's going to be able to present at Geoconfluence. And so we think it's very important to have the student involvement here at the conference. And we look forward to our next speaker, who is one of the students from Missouri SMT. Xing will be discussing the use of flash and polymers to stabilize soils, which should be an interesting topic, I'm sure. He is, as I said, he's a Missouri SMT graduate student. He received his his master's degree, and he's now working on his PhD at the school. Can everyone hear in the back?
Okay, good afternoon everyone. My name is Jing Kang. I'm a graduate student in Kerala, and my advisor is Dr. Bate. He's an assistant professor in Kerala. And here is our research team and some of our newly developed soil testing device. And today I'm going to talk about my PhD research, which is using high volume of flash in geotechnical engineering by controlled organic additives. My presentation outline has 5 parts. First part is the introduction, my research motivation, the polymers, materials that I'm going to use. Second part is a segmentation test results, which includes how to select the polymers and some interesting results. The third part is the microscopic study and some physical chemical properties of the organically modified flash soil mixtures. And fourth part, I will show you some Atterberg limits test results and the triaxial compression behaviors of the modified flash soil mixtures. And finally, I will give you a short summary of my research. Introduction part. Every year, large quantities of coal is being used in thermal power plant and to generate electricity for us. At the same time, a lot of flash has been generated, and normally we deal with this flash. We throw them into the but this gives us a lot of environmental problems. And also, for example, the Kingston triaxial failure in the flash slope failure happened in 2008, which caused very serious damage to the neighborhood. In the civil engineering practice, flash could be used as deep soil mixing, soil replacing, and soil stabilization. However, most of those applications are for Class C flash, because the Class C flash has very good self-cementations, and they could reduce the plasticity of a soft soil, increase the shear strength, and decrease the shrink swell potential. I have done a little bit literature review, and I found in road-based or sub-based pavement and soil stabilization, only 2.8% flash and 0.1% are being used. Their recycle rate is really low. And because there were some problems and challenges in high volume reuse of flash, for example, the flash are heterogeneous from one power plant to another, and they're not, their chemical compounds varied. And also another thing is the water content change, the flash mechanical property will change a lot. And also, if you use high volume of flash, it will give us like environmental problems, like the heavy metal ions leaking, cause some environmental problems. In recent years, some researchers using organic agents to stabilize soft soil. This organic agents could increase the shear strength, stiffness, and increase the coastal and wind resistance of the soil. By thinking about using the polymer, I was thinking to polymers into the fly ash soil mixture so that the polymer kind of work as a binder to biting or stabilize the fly ash soil mixtures. The fly ash I'm using here is class F fly ash. Those fly ash has barely no self-cementations. So I'm trying to use the organic polymers to bind the soil and with the fly ash so that to increase the overall performance. And I have done a literature review and found those polymers, for example, polyacrylamide, xanthan gum, sodium lauryl sulfate, those are the popular polymers used by previous practitioners. So I found those polymers and tried to select the best one for soil stabilization. First part, I'll show you some instant action of the polymers. So we put xanthan gum with Ottawa sand, and I shape the soil to a cylinder. And if the soil of the Ottawa sand with polymer, it can stand upright, straight like this. But if the sand without polymer, only the sand with water, it's hard to form a cylinder and easily to be collapsed. And you could play the sand in hand. So basically, the polymer can immediately increase the cohesion of the soil, so the soil can be shaped or formed into a cylinder. I have purchased those polymers from Thermo Fisher, and polymers generally have a high molecular weight. And another feature of those polymers is normally has a long chain or long tail. And one important function group is the hydroxyl function group. This one could easily be dissolved into the water. And in the water, those long chains could interwoven or interlink with each other. And the pan of the polymer can be absorbed to the clay surface, and with their tails pointing out into the water, and their tails can interlink, so form a branching between particles, so that we can increase like in the macro scale, its strength could be increased by the interwoven or interlink network of those polymers. This picture is a SEM image of the fly ash particles. Fly ash particles are normally sphere-like or pretty round. They are ranged from like few microns to like even 100 micrometers. And if I put the fly ash into water, the conductivity of the water increases as the fly ash content increases, because the fly ash could be hydration and release some ions into the water. And the kaolinite particles are totally different from the fly ash particles. Kaolinite particles are plate-like. It's pretty flat. And I purchased the Georgian kaolinite. It's a very pure and clean clay mineral. Normally, the kaolinite aggregates range from 0.1 micrometer to 4 micrometer. Sedimentation test. We perform sedimentation tests in this kind of cylinder. Before the sedimentation starts, the suspension is well mixed in a cylinder, and after test, you could see the top part is clear water, and the bottom part is the sediments. And through this sedimentation test, we can model the dewatering behavior of the soil. Like we can also model the draining fluids, the stability of the borehole draining fluids, or transport evaluate the sedimentation speed, sedimentation mode, fabric, the mixtures fabric, and like the settling rate. And also, this test is simple. We can perform large, like so many tests, and find out which polymer is the best to dewater rate or to fast the settling rate, and find the best ratio and candidate for soil stabilization. In my research, I have built a large sedimentation panel. This panel has 2 shelves. Each shelf I can put 14 cylinders. So total I can run 28 sedimentation tests at one time. And I'm using a camera to take time-lapse photos to monitor the interface change over time, and then reduce the data on computer. Generally, there are 2 types of settling or sedimentation. Top cartoon here shows the dispersed settling, which means the sedimentation is governed by the Stokes law. Large particles settle at the bottom, to the bottom, and small particles suspending the suspension. And the final sediment volume increases with time, you can see, and the suspension gets clearer and clearer over time. Another type is flocculated settling. If you add salt or polymer, they induce flocculation of the suspension, and the soil settles as a whole part. There's only one interface between the clear water and the sediment. But this one, we have 2 interfaces. One is top, one is bottom. Here's a group of pictures showing 2 types of the sedimentation mode. Left, kaolinite mixed with salt at different concentrations. Left 3, you could see as flocculated settling. The final volume, sediment volume, decreases over time. And this 3 cylinders shows you a dispersed settling. The final volume increases over time. And I have plotted the data in these 2 plots. This part, as I showed here, the interface decreasing over time, and this part, the interface increase with time. And the 0.003 molar per liter is a transition zone. If the concentration is higher than this, all the soils are flocculated or aggregated, settles very fast. But if the salt concentration is really low, it settles in this dispersed form. And if you do 2 tangent lines, one line through the steep part, the slope, another line through the tail part, there is an intersect at here. The corresponding time is called TS. Some researchers call this time soil formation time. So which means if the time is over or larger than this time, we could consider the bottom part as a real soil, or it has a strength. But if the time is less than this time, there are like a slurry or suspension. So basically, this time can help us evaluate how fast the soil forms. And the left picture here shows the sedimentation behavior of kaolinite in PEO solution. The PEO is a neutral polymer. It attached or being absorbed to the clay surface and induce flocculation. So the soils settle very fast and in a flocculated form. But if we put soil into the SLS solution, the soils are dispersed or repulsive to each other. And the soil formation time is pretty much large, 150,000 seconds. So this one only 2,000 seconds. And the reason is this organic is polymer. So when the kaolinite is also negatively charged. So if you put kaolinite in this solution, the repulsion force between kaolinite particles even larger or increased. So particles are repulsive by each other and settles very slow. But this one, the polymer be absorbed into the clay particle and compress the double layer. So particles kind of aggregated and settles fast. So now let's look at some SEM images of the soil. I put 1% Zensen gum, and you could see high degree of aggregation induced by the polymer. And if we zoom out, like we can, at a 20 micro scale, you could see all those big aggregates there. Similarly, if we look at the fly ash soil mixture, fly ash particles, if only fly ash with the kaolinite are surrounded, like the fly ash are surrounded by the kaolinite particles. And if the fly ash kaolinite mixture with 1% Zensen gum and soil are aggregated, and if we look at that 50 micrometer scale, you can see fly ash, soil, they all be bonded or bridged by the polymers, and they work as a unit or integrity system. I also measured the zeta potential of the kaolinite particles. The zeta potential is an indicator of the net surface charge of a soil particle. The net surface charge directly reflects the particle interforce. If the zeta potential is very high, which means particles are repulsive by each other. If the zeta potential is 0, which means the attractive force between two particles are dominant. So for salt and for the HDTMA, at high concentration, they all compress the double layer and increase the zeta potential to almost 0, which means at high concentration, the zeta potential are relatively high, around 0, and particles try to be attractive to each other. So this reflects the attractive force dominant and particles aggregates. And also I measured the gray size distribution in the suspension and the sediment parts. And I plotted the mean particle size versus the salt concentration. As you could see, at very high concentration, the particles are generally large. The aggregates are large, but at small concentration, the measured size are small. So this all, combined with the SEM image, shows that at high concentration, the soils are aggregated and by bridging or bonding by the polymers. And here is some Atterberg limits change, liquid limit and plastic limit change versus the percentage of fly ash. Normally they decrease as the fly ash percentage increase. So how is the plasticity index change? We can see the PI also increase as the percentage of fly ash increased. Some stress strain behaviors in the triaxial compression test. This picture is 100% kaolinite. They all have the dilation and stress softening behavior. But if we put fly ash in the soil, the shear strength increase and the critical state friction angle also increase by adding fly ash. However, if we put salt, like 1 molar salt into the kaolinite, the dilation behavior disappears. All the salt and the shear strength also increase is higher than this one. And if we have fly ash soil and mixtures and the soil. Normally, the kaolinite has a 18.2 degree of friction angle, but the kaolinite with salt friction angle changes to 26.7. So the major contribution, I think, is the salt-induced aggregation, so the particles or aggregates are larger at this condition. So this contributes to the critical state friction angle. For the flash soil mixture, the friction angle is 24.8, and for the polymer stabilized flash soil mixture, the friction angle is 26.6. But you might notice that it has a relatively low coefficient of regression, which means if I force this line to go through zero, it's not a good method because it has a cohesion here. So what I can conclude here is the polymers obviously contribute a lot to the cohesion of the soil, and the addition of the salt induces the aggregation. And here is a short summary of my research. I evaluated the sedimentation behavior, the ionic stress on the sedimentation behavior, and found some polymers are good at sedimentation. And the gray size analysis results, the SEM results, they all help me to understand the stabilization mechanism and the stress scale of the organically modified flash soil mixtures. So I think that's the end of my presentation. I really happy to answer questions if you do have. Okay, that's all.
Any questions?